The document that nearly strangled the TSR-2 in its cradle ran to 15 pages and bore the signature of Duncan Sandys, Minister of Defence, dated the 4th of April 1957. Command Paper 1-2-4, presented to Parliament that spring, declared that manned military aircraft were approaching obsolescence and that guided missiles would assume the principal burden of British air power within a decade. The Royal Air Force, the paper argued, required no further generation of strike aircraft beyond the V-Force already in service at Marham, Scampton and Honington. For the design offices at Weybridge, Wharton and Preston, the white paper read like a death warrant. Yet within the Air Ministry on King Charles Street, the chiefs had quietly begun work on a requirement that contradicted Sandys before the ink had dried. General Operational Requirement 339, drafted in the autumn of 1956 and circulated in revised form in March 1957, called for a tactical strike and reconnaissance aircraft to replace the English electric Canberra across both the Royal Air Force and the Royal Australian Air Force. The Canberra B Mark II, for all its virtues at 30,000 feet, could not survive the surface-to-air missile belts. The Soviets had begun deploying. In East Germany, following the introduction of the SA-2 guideline in 1957, Francis Gary Powers and the Lockheed U-2 would prove that point conclusively over Sverdlovsk on the 1st of May 1960. The Air Staff understood the implication earlier than most. Air Vice Marshal Geoffrey Tuttle, then Deputy Chief of the Air Staff, pressed the case at successive Defence Board meetings that high-altitude penetration was finished. The future, he insisted, lay in low-level ingress beneath the radar horizon at speeds and altitudes that demanded an entirely new airframe. The minutes of the Operational Requirements Committee for the 7th of November 1957 record his exact phrasing, that the service required an aeroplane capable of destroying a precise target on first attack, by day or night, in any weather, from low level. That single sentence became the foundation stone of the entire programme. It was not a wish list. It was a tactical doctrine, compressed into a procurement specification, and it ran directly counter to the Sandys orthodoxy that the Treasury was busy enforcing across every other corner of British defence spending. The contract competition that followed, conducted through 1958, narrowed 9 industrial submissions to 2 genuine contenders. Vickers-Armstrongs at Weybridge offered a refined development of their Type 5 7-1 design study. English Electric at Wharton submitted the P-17, a slender twin-engined design with shoulder-mounted wings and a pronounced nose droop. Neither firm possessed the resources to build the aircraft alone. The Ministry of Supply, under pressure from Aubrey Jones, and later from his successor, Reginald Maudling, forced a shotgun marriage. On the 1st of January 1959, the British Aircraft Corporation came into being, with the TSR-2 as its founding programme and its founding burden. The agreement was signed at Shellmex House on the Strand. Sir George Edwards of Vickers and Lord Caldecote of English Electric divided the work between Weybridge and Wharton, with final assembly at Samlesbury in Lancashire. The Treasury approved an initial development figure of £90 million. By the time the cancellation telegram was drafted, 6 years later, that figure had multiplied fourfold, and every shilling of it had been spent in the shadow of the Sandys white paper that had pronounced the entire enterprise unnecessary before it had begun. The specification that landed on the desks at Wharton in March 1959 was, in the candid assessment of Sir Sidney Cam at Hawker, the most demanding requirement ever issued to the British aircraft industry. That verdict was not hyperbole. General Operational Requirement 339, in its final endorsed form, demanded performance figures that no aeroplane in service anywhere in the world then approached, and several that no aeroplane has matched since. The numbers themselves bear repeating slowly. A combat radius of 1,000 nautical miles, carrying a 2,000-pound store, with the final 200 miles of ingress flown at 200 feet above ground level, dash speed of Mach 1.1 at sea level, high altitude transit at Mach 2.05 at 50,000 feet, takeoff run of 600 yards from a rough, unprepared strip no longer than a stretch of West German Autobahn. The aircraft was to operate from grass surfaces of a California bearing ratio of 6, which in plain English meant cow pasture. It was to be airborne and serviceable within 15 minutes of an alert call from the Tactical Operations Centre at Rheindahlen. Each of those figures, taken individually, sat at the outer edge of contemporary aeronautical possibility. Taken together, they appeared to violate the laws by which aeroplanes were known to behave. The English Electric Lightning F Mark 1, then entering service at Coltishall, could approach Mach 2 but only at altitude and only with full reheat, draining its fuel in roughly 6 minutes. The Buccaneer S Mark 1 at Lossiemouth could drop to 50 feet over the North Sea, but managed barely Mach 0.85 at that height. The Americans had nothing remotely comparable. The North American A-5 Vigilante came closest, and its operational record at low level was, to put it gently, troubled. The reconnaissance demands were equally severe. Specification RB 192D, issued as a companion document, required the aircraft to carry a sideways-looking airborne radar of Q-band frequency, capable of resolving a tank-sized target at 40 nautical miles slant range, a forward-looking infrared line scan, and a vertical camera fit producing imagery of sufficient resolution to identify individual rolling stock at a Polish marshalling yard. All of this was to be processed and ready for ground exploitation within 90 minutes of touchdown at Laarbruch, or Bruggen. The political weight behind the specification was extraordinary. Sir Thomas Pike, Chief of the Air Staff from 1960, refused to countenance any reduction in performance and made the point personally to Harold Watkinson at the Ministry of Defence on the 17th of February 1960. The minute of that meeting, now in file Air 8, stroke 2276 at Kew, records Pike stating that any compromise on the low-level dash requirement would render the aircraft useless against the Warsaw Pact's second-echelon armoured formations, which were the targets that justified the programme in the first place. What the air staff wanted, in effect, was an aeroplane that could fly from RAF Wildenrath in the early hours of a hypothetical war, sprint at treetop height across the inner German border, navigate by terrain reference past the Brocken Massif, deliver either a red-beard tactical nuclear weapon or a stick of conventional 1,000-pounders onto a Soviet pontoon bridge across the Elbe, and be back on Dutch concrete before the orbiting MiG-21s had registered the intrusion. The specification did not describe an aircraft. It described a tactical certainty. The men at Wharton were now required to translate that certainty into rivets, titanium, and aluminium alloy. The airframe that emerged from the drawing offices at Wharton during 1960 and 1961 was unlike anything previously built in Britain. The fuselage measured 89 feet from pitot tip to jet pipe, with a wingspan of only 37 feet and 1 inch. The wings themselves were tiny in proportion to the body, sharply tapered with a quarter-chord sweep of 60 degrees on the leading edge inboard, reducing to a gentler angle outboard, and tipped with the characteristic anhedral droop that gave the aircraft its hunched, predatory silhouette on the apron at Boscombe Down. That stubby wing was the answer to a tactical equation. A larger wing offered better field performance and longer range, but at 200 feet over the North German plain, it would have transmitted every gust and thermal directly into the cockpit, shaking the navigator's mapping radar into uselessness and the pilot's spine into pulp. The Wharton aerodynamicists, led by Ray Creasy, calculated that a high wing loading somewhere above 120 pounds per square foot would smooth the ride at sea level to the point where crews could function for the full ingress run without losing visual reference or fine motor control. The wing they designed was the smallest that the takeoff requirement and the structural margins would permit. The structure itself was an engineering departure of the first order. Roughly 12% of the airframe by weight was titanium alloy, principally in the engine bay frames, the rear fuselage skins around the jet pipes, and the wing root attachments, where temperatures during sustained low-level dash were calculated to reach 200 degrees Celsius. British Aircraft Corporation engineers at Samlesbury had to develop entirely new machining techniques. The Lancashire factory floor, in 1962, was, in places, the most advanced metalworking environment in Western Europe, with Marwin profilers cutting wing spars from solid billets in single operations that took 30 hours apiece. The propulsion was the second pillar. The Bristol Siddeley Olympus Twenty-Two-R, a developed and reheated descendant of the engine that powered the Vulcan B Mark II, delivered 30,710 pounds of thrust in afterburner, and just over 19,000 dry. Two of them, mounted side by side in the rear fuselage, gave the aircraft a thrust-to-weight ratio approaching unity at combat weight. The same engine family, in its Olympus 593 form, would later carry Concorde to Mach 2 over the Atlantic, but its first full reheat trials were conducted not at Filton, but in a test cell at Patchway during 1962, and the early development was dogged by a low-pressure turbine resonance that destroyed the test rig spectacularly on the 3rd of December that year, killing one technician and delaying the engine program by 8 months. The undercarriage was the third unusual feature. To meet the rough strip operating requirement, Electro-Hydraulics of Warrington produced a tandem wheel main gear that retracted forward and inward into the fuselage, leaving the slender wing structurally untroubled by gear loads. The tyres were of a low-pressure design developed jointly with Dunlop, capable of absorbing the impact of grass and pierced steel planking without bursting. Trials at Boscombe Down in late 1964, conducted on a deliberately roughened taxiway, demonstrated that the aircraft could make 20 consecutive landings on simulated, dispersed strip surface without any structural inspection beyond a routine walk-round. No British combat aircraft, before or since, has matched that figure, and no Warsaw Pact analyst studying the photographs published in Flight International that December failed to grasp its implication. The promise of first-pass destruction did not rest on the airframe or the engines. It rested on a black box, roughly the size of a writing bureau, built by Ferranti at their Crewe Toll plant in Edinburgh, and on a partner box from Elliott Brothers at Borehamwood. Together they constituted what the air staff in their internal correspondence simply called the system. Without it, the TSR-2 was a fast aeroplane. With it, the aircraft became something the Royal Air Force had never possessed, and would not possess again until the Tornado GR Mark I entered service at Honington in 1982. The forward-looking radar, designated FLR by the Project Office and built around a Q-band transmitter operating in the 8 to 12 GHz region, performed two distinct tasks in alternating scan modes. In ground mapping mode, it produced a rolling presentation of the terrain ahead, which the navigator in the rear seat used to fix the aircraft's position against preloaded target imagery. In terrain following mode, the same antenna scanned a narrow vertical pencil beam ahead of the aircraft, measuring the height of approaching ground features and feeding those returns into the autopilot. The pilot's task during a low-level run was, in theory, reduced to monitoring instruments. The aeroplane flew itself across the contours of Central Europe. The terrain following calculation was performed by the Verdan computer, an American-derived digital unit license built in Britain by Elliott Automation. Verdan stood for Versatile Digital Analyzer, and the unit installed in the TSR-2 ran at a clock speed of roughly 140 kHz, with a memory of 8,000 26-bit words held on a rotating magnetic drum. By the standards of 1963, this was formidable computing power. By the standards of a modern wristwatch, it was negligible. Yet it was sufficient to solve the terrain following equation 30 times per second, and to drive the autopilot servos with a response lag of under 100 milliseconds. The set clearance height was selectable in the cockpit. 200 feet was the standard cruise figure for transit. 100 feet was available for the final ingress to a defended target. Trial profiles flown over the Pennines during 1964, with a modified Canberra carrying the prototype Ferranti kit, demonstrated that the system could hold height to within plus or minus 15 feet of the selected datum at speeds up to 580 knots in cloud at night. The Boscombe Down Trials report of November that year. A and AEE, document 764/64, recorded the system as fully meeting the operational requirement, and added the dry observation that no comparable equipment was known to exist in any other air force. Target acquisition was handled by the sideways-looking radar mounted in two long fairings on the lower fuselage, supplemented by a moving target indicator capable of distinguishing a tracked vehicle from background clutter at ranges exceeding 30 miles. The navigator's display in the rear cockpit allowed him to designate a target with a rolling cursor, at which point the attack computer assumed the offset bombing solution. The pilot then had only to maintain the steering bar centered on his head-up display, a Specto Mark II unit that was itself a British first, until weapon release. The accuracy specification was a circular error probable of less than 100 feet at the release point. Trials with a representative inert store at the Aberporth range during early 1965 suggested the actual figure was nearer 50. For a tactical nuclear weapon of the Red Beard class, this was overkill. For a conventional 1,000-pounder dropped on a railway bridge at Magdeburg, it was the difference between strategic effect and wasted ordnance. The bomb bay measured 20 feet in length and could swallow stores in combinations that no other tactical aircraft of the period could match. Its design had been driven by a single specific weapon, and then progressively widened to accept the entire spread of British tactical ordnance. Then in development at the Royal Aircraft Establishment at Farnborough, and the Atomic Weapons Establishment at Aldermaston. The weapon that had defined the bay's dimensions was Red Beard, the Mark I tactical nuclear bomb, which had entered service with the Royal Air Force and Royal Navy in 1962. Red Beard was a free-fall implosion device of approximately 15 kilotons yield in its Mark II form 12 feet in length, weighing 1,750 pounds, and it represented the bridge between the strategic Yellow Sun megaton. Class weapons carried by the V-Force and the smaller battlefield stores under development for 1960s tactical use. The TSR-2 bomb bay was sized initially. Around 2 Red Beards carried in tandem a payload that gave a single aircraft the destructive equivalent of roughly 30,000 tons of conventional explosive delivered, with a circular error probable of 50 feet. By the time of the cancellation, the planned operational fit had moved on. Red Beard was being phased toward replacement by the WE-177, a lighter and more flexible parachute-retarded laydown weapon developed at Aldermaston during the early 1960s. The WE-177A, the tactical variant of approximately 10 kilotons, was specifically designed for delivery in the TOS profile that the TSR-2's attack computer was programmed to fly. The aircraft would approach the target at 200 feet, pull into a 4G climb at a precisely computed range, release the weapon on an upward arc, and then break hard away, while the bomb continued ballistically to its apogee before descending under retardation onto the target. The pilot would be 12 miles distant and accelerating when detonation occurred. Conventional payloads were equally varied. 6 1,000-pound general-purpose bombs could be carried internally, with provision for a further 4 on underwing pylons that the production aircraft would have featured. Trials at the Proof and experimental establishment at Showburiness during 1964 had confirmed that the bay's ejector release units, manufactured by ML Aviation at White Waltham, could clear a stick of 6 bombs at half-second intervals at speeds up to 600 knots without store collision. Cluster munitions, principally the BL-755 anti-armour weapon, then under development at Royal Ordnance Glasgow, were specified for the anti-tank role against second-echelon Warsaw Pact armour. The reconnaissance pack was a separate matter entirely. A purpose-built fairing, designed to fit into the same bay attachment points as the weapons load, carried a comprehensive sensor fit drawn up to specification RB. 192, 2F, 95 oblique cameras of 48-inch focal length, manufactured by Williamson Manufacturing at Reading, covered the medium-altitude regime. An EMI Type 401 sideways-looking airborne radar provided all-weather coverage of a 20-mile swath either side of track. A Hawker Siddeley Dynamics line-scan unit, operating in the 3 to 5 micron infrared band, produced thermal imagery of sufficient resolution to detect a recently used vehicle hide beneath forest canopy. What this combined armament represented in cold operational terms was an aircraft that could carry a strategic nuclear warning, a conventional precision strike, and a comprehensive intelligence gathering capability on the same airframe, dispatched on the same sortie, against the same target. The Soviet General Staff, studying the published outlines of the program during 1963, understood precisely what that combination meant for the survivability of their forward formations. Soviet military intelligence interest in the TSR-2 program was neither casual nor speculative. The GRU station, operating under diplomatic cover from the Soviet embassies at Kensington Palace Gardens, had identified the project as a priority collection target by late 1960, and the Warton Aerodrome in Lancashire became the focus of a sustained and patient intelligence effort that continued until the cancellation. Files released by the Czechoslovak STB archive after 1989, and partially corroborated by the Mitrokhin material, lodged at Churchill College, Cambridge, indicate that at least 3 separate human source operations were directed against British Aircraft Corporation personnel between 1961 and 1964. The Soviet concern was specific and technically grounded. Air defence planning in the Western Group of Forces, headquartered at Wunsdorf-Sossen, south of Berlin, rested upon a layered system, whose engagement parameters were known with some precision to British Signals Intelligence at GCHQ Cheltenham. The forward belt comprised S2 guideline batteries deployed around airfields, command bunkers and bridge crossings, with a minimum engagement altitude of roughly 3,000 feet and a minimum range of approximately 8 kilometres. Below that altitude and inside that range, the SA-2 was effectively blind. The system's fan-song fire control radar, operating in the E and F bands, suffered severe ground clutter problems against any target below 500 feet. The point defence layer was constituted by the ZSU-57 anti-aircraft gun, and from 1965 onward, the ZSU-23-4 Shilka. Both were optically directed at the time. The TSR-2 was under development, with radar augmentation only on a small proportion of vehicles. Their effective engagement window against a target transiting at 580 knots and 100 feet was, by Soviet General Staff analysis, of the order of 7 seconds. Inside that window, the gunner had to detect the aircraft visually, slew the mount, lay the sight and fire. Soviet exercise data from the late 1950s recovered in fragmentary form by Western intelligence, and now held at the National Archives in file DEF 31/194, indicated hit probabilities below 5% against simulated low-level targets at those parameters. The interceptor layer was no more reassuring to Moscow. The MiG-21 F-13, the principal frontal aviation fighter of the period, possessed limited look-down radar capability and depended upon ground-controlled interception for target acquisition. Against an aircraft running at 100 feet through ground clutter, with the Ferranti FLR feeding terrain following commands, and the autopilot threading the contours of the Harz Mountains, the GCI controller at a Soviet radar station would simply lose the contact within 30 seconds of border crossing. The Yakovlev Yak-28P, then entering service, offered marginal improvement, but no genuine answer. The conclusion drawn by Soviet air defence assessments, of which a partial summary reached the West through the Penkovsky material before his arrest in October 1962, was uncomfortable. A TSR-2 force of the planned 158 aircraft, dispersed across Royal Air Force Germany and the United Kingdom, would be capable of striking targets as deep as Brest-Litovsk and Lvov on a single sortie, with a probability general staff calculated at above 80%. The aircraft's combination of dispersed operation, low-level dash, terrain following, automation, and first-pass accuracy meant that the standard Soviet counter-air doctrine, which assumed the destruction of NATO airfields in the opening hours of war, became largely irrelevant. There were no fixed airfields to destroy. That assessment, more than any tactical calculation, defined Moscow's quiet and persistent interest in the cancellation arguments then unfolding within Whitehall. The Soviet General Staff did not need to defeat the TSR-2 in the air. They needed only to encourage its defeat in the cabinet room. The cancellation, when it came, was not a single decision, but the culmination of 18 months of attritional warfare between the Treasury, the Air Ministry, the new Ministry of Aviation, and a Labour government that had inherited the programme from its Conservative predecessors and disliked it on both fiscal and ideological grounds. Harold Wilson's administration took office on the 16th of October 1964, with Dennis Healey at Defence and James Callaghan at the Exchequer. The TSR-2 file landed on Healey's desk within his first week. The Treasury estimate for the programme had by then risen to roughly £750 million for a force of 150 aircraft, against the original £90 million development figure, approved in 1959. The unit cost, depending on which method of accounting one accepted, ranged from £2.5 to £5 million per airframe, at a time when a Lightning F Mark VI was costing the service approximately $1,200,000. Healey's hostility to the programme was personal as well as professional. He had taken the view, expressed in private correspondence with Solly Zuckerman, the government's chief scientific advisor, that the British aircraft industry was producing aeroplanes designed for the wars of the Royal Air Force's institutional preference rather than the wars the country was likely actually to fight. The Cabinet Defence and Overseas Policy Committee minutes of the 1st of February 1965, held now in Cab 148 at Kew, record Healey arguing that the strike role required by the TSR-2 specification could be discharged more cheaply by acquiring the General Dynamics F111A from the United States, then in advanced development at Fort Worth, Texas. Robert McNamara had made the offer formally during a visit to London in late January 1965. The American proposal was an option agreement to purchase up to 110 F111K aircraft, a variant tailored to British requirements, at a unit cost claimed to be £2.25 million, and with an offset arrangement intended to cushion the impact on British industrial employment. The figures, in retrospect, were wildly optimistic on both sides of the Atlantic. By 1968, the F111K cost had escalated beyond the cancelled TSR-2 figures, and the British order itself was abandoned. The decisive cabinet meeting was held on the 1st of April 1965. The discussion lasted 4 hours. Roy Jenkins, then Minister of Aviation, defended the British programme with conviction, but without conclusive figures. Callaghan presented the budget the same afternoon and announced the cancellation in the House of Commons during his speech, in a single sentence buried among broader expenditure measures. The text read simply that the government had decided not to continue with the development of the TSR-2. What followed at Samlesbury and Warton has entered British industrial folklore. Within weeks of the announcement, instructions arrived from the Ministry of Aviation that the production jigs, the assembly tooling, and the partially completed airframes on the Samlesbury line were to be destroyed. The order was carried out with a thoroughness that suggested deliberate policy rather than administrative tidiness. Photographs taken by workers on the line, some now held at the Brooklands Museum at Weybridge, show the jigs being cut up with oxyacetylene torches during the summer of 1965. Only 2 complete airframes survived. XR-220 went to the Imperial War Museum at Duxford. XR-222, the aircraft that had flown 24 test sorties from Boscombe Down, was preserved and now stands at the Royal Air Force Museum at Cosford. The remainder were broken for scrap. The strategic consequences of the cancellation were felt within Royal Air Force Germany almost immediately. The Canberra B Mark 16 and B Mark 8 squadrons at Larbrook and Bruggen, which the TSR-2 had been designed to replace, soldiered on into the early 1970s in a low-level strike role, for which they had never been intended. The aircraft's operational ceiling for survival against the Warsaw Pact air defence environment by 1968 was roughly 250 feet, a figure the Canberra could achieve only at the cost of severe airframe fatigue. Wing spar replacements at number 5. Maintenance unit at Kemble became a routine industrial activity throughout the late 60s. The interim solution adopted after the F111K cancellation in January 1968 was the McDonnell Douglas Phantom FGR Mark II, ordered in modified form with Rolls-Royce Spey engines and British avionics. The Phantom was a competent aircraft, but not a TSR-2. Its combat radius in the strike role was barely 400 nautical miles against the 1,000 specified for the British design. Its low-level penetration speed was lower. Its accuracy was inferior. It had no terrain following capability worthy of the name. The Royal Air Force used it because it had nothing better, and because political circumstance had removed the choice. The longer-term answer was the Panavia Tornado GR Mark I, developed under the Multi-Role Combat Aircraft Program, initiated in 1968 as a tripartite effort between the United Kingdom, West Germany, and Italy. The Tornado entered service at Honington in 1982, fully 18 years after the cancellation of the British aircraft it was effectively replacing. It carried Ferranti terrain following radar that descended in concept directly from the TSR-2 system. It dropped to 200 feet at 540 knots in the same strike profile the earlier aircraft had pioneered. Its accuracy specifications were comparable. Its combat radius was shorter, its weapon load was smaller. It was, by any honest measurement, a tornado-shaped TSR-2 built 2 decades late and shared 3 ways. The Soviet documentary record, declassified in fragments since 1991, confirms what had been suspected at the time. The General Staff of the Soviet Armed Forces, reviewing the British cancellation in the late spring of 1965, judged it a strategic windfall of the first order. A Vojenno-Vozdushnyi Sily assessment, dated the 11th of May 1965, located in the Russian State Military Archive in Fond 500 at Podolsk, and partially translated for Western publication during the 1990s, recorded the conclusion that the cancellation removed the principal NATO conventional strike threat to second-echelon armoured formations west of the Vistula until at least the late 1970s. The assessment estimated that this gave the group of Soviet forces in Germany an effective decade of operational latitude that no expenditure on additional air defence systems could otherwise have purchased. What Britain had cancelled was not merely an aeroplane. It was a tactical doctrine, an industrial capability, and a strategic deterrent rolled into a single airframe. The Ferranti and Elliott engineers, who had built the world's first operational terrain following radar, dispersed to other programs or to other countries. The titanium machining capability at Samlesbury was wound down. The aerodynamic research that had produced the high-wing loading, low-altitude airframe was filed and forgotten. The Royal Air Force entered the 70s with no equivalent capability. And, when the Tornado finally arrived, with the uncomfortable knowledge that it had paid twice for the same answer. The 2 surviving aircraft at Cosford and Duxford remain the only physical evidence of what was, by any technical reckoning, the most advanced strike aircraft of its generation.